Hello, my name is Heiko. I'm a PhD student at MPI-SWS in Germany. Today I want to tell you about our new HOL4 tactic language framework called Lassie. But before going into its details, I want to answer a simple question. Why do we need another tactic language framework? There have been a number of successful projects using interactive theorem proving in the last few years. Just to name a few, in the area of compilers, we have the ComCert and CakeML verified compilers. Then there is the HOL4 verified microkernel. Or in the area of mathematics, we have the proof of Kepler's conjecture in the Fleischberg project and the proof of the four-color theorem. But all of these big projects come at the price of a steep learning curve that is usually involved when picking up a new ITP system. Why is this the case? On the left-hand side of the screen, I'm showing you an example math theorem and below of it a start of how you would write the proof just in plain English. And on the right-hand side of the screen, you see its HOL4 equivalent with a proof. But please, for now, don't bother reading all of it because this is just for illustration purposes. As one can easily see, just the theorem statement itself has a straightforward translation into HOL4 syntax. So the main difficulty in improving this theorem actually lies in performing the proof itself. So the complexity in picking up a new ITP system also lies in these proofs. Why is this the case? Why are these proofs hard to perform? Let's look a bit closer. On the one hand, what you always have to know, even just when doing a proof with pen and paper, is the necessary proof steps that you want to do to show the theorem. On the other hand, what is inherent for any ITP system is that you have to know the tactics that correspond to these proof steps. So there's two things involved here. You need both detailed knowledge of the involved proof steps and the tactics representing them. There have been past attempts at alleviating this issue by developing different styles or kinds of tactic languages. So let's take a closer look at those. On the one end of the spectrum, we have so-called expert systems like the SS Reflect and LTAC languages for Koch or the Eisbach language for Isabelle and Hall. They give fine-grained control over the proof steps that are performed and have very rich and expressive languages that can be used in many different use cases. The downside being that for a novice user, these have an overwhelming number of features which can make it hard to pick up these languages in the first place. On the other end of the spectrum, we have natural language interfaces like Naproche SAD or the MESAR system. These have straightforward interfaces and provide a simple language which is easy to use for novice users. However, these languages do not interoperate with the plain tactic languages used by the ITP systems. Our tactic language framework Lassie sits right in the middle of this spectrum, and I will show you now why this is the case. So as an example, suppose we want to define this tactic in Lassie where we say instantiate for all x, p of x with true. An expert user can now define this as the HOL4 equivalent by example giving this tactic as a single instance of a general one we would like to use. By using an extensive semantic parser, Lassie will now automatically generalize this into the general tactic instantiate term with term, and such that we get a domain-specific tactic language that can be used by novice and expert users alike. Let's look at how Lassie can help you with performing a proof in a bigger example. Suppose you would want to teach HOL4 in a class. I'm showing you on this slide Euclid's theorem, proven both with a plain HOL4 proof on the left-hand side and the Lassie proof on the right-hand side. We think that the Lassie proof is more appealing to a novice user and makes it easier to grasp the proof steps, where you can then later on elaborate and learn the tactic language of HOL4 in a second step. To summarize, our paper provides an interactive and extensible framework, Lassie, for defining tactics by example. We show an example implementation in the HOL4 Theorem prover, which is available on GitHub and in the process of being integrated into the HOL4 Theorem prover. Our paper also shows a number of case studies and a HOL4 tutorial, which is also available on GitHub, to showcase the effectiveness of Lassie. Through the rest of the talk, I want to go through 3 main points. I will first show you how Lassie is used by explaining you its 3 main components: NLTAC, NLExplain, and def. Then I want to quickly go over the key design decisions why semantic parsers are useful for developing tactic languages for theorem provers. And finally, I want to summarize the case studies in our HOL4 tutorial showing how Lassie can define and reuse tactics in bigger proofs. Let's start by how Lassie is used. So, as a quick overview, Lassie has 3 main entry points. The first one being NLTAC, which acts as a drop-in replacement for HOL4 tactics. We have NLExplain, which can then be used to translate or to understand what the HOL4 tactic underlying a Lassie tactic is. And finally, there is def, which allows to extend Lassie with custom tactic descriptions. Let's look at an example for NLTAC first. In this example, I will show you how to use NLTAC in an interactive HOL4 proof. On the left-hand side of the screen, you can see an example theorem showing that if x and y are positive, then the inverse of x is less than or equal to the inverse of y, if and only if y is less than or equal to x. On the right-hand side, you can see an interactive HOL4 session in which we have already started an interactive proof of the theorem. In a first step, we will introduce assumptions using the exact same Lassie tactic by first marking it and then sending it to the interactive HOL4 session. As you can see, it introduced the 2 assumptions numbered 0 and 1, which prove that x and y are positive. Now, in the next step, I will demonstrate another tactic which allows us to enrich the list of assumptions with additional proofs. For this, we will apply the Lassie tactic. We show that the inverse of x is less than the inverse of y exactly if y is less than or x, using and then a small proof script. We do this by marking the tactic and sending it to the HOL4 session. As you can see, it added the additional assumption numbered 2, and from this whole example, you could see that NLTAC works as a drop-in replacement for HOL4 tactics. Let's take a closer look at how NLTAC works. So when we give our tactic on the top left of the slide to the Sempre semantic parser, which is used internally by Lassie, what it will do for us when using NLTAC is it will translate it into its HOL4 equivalent and apply this tactic to the goal for us. So NLTAC just acts as a drop-in replacement for HOL4 tactics. Having seen NLTAC, let's look at NLExplain next. In this example, I will show you how Lassie's function NLExplain works. As you will see, NLExplain is a perfect fit for understanding how Lassie's tactic descriptions map to HOL4 tactics. On the left-hand side, you see, as before, an example theorem, and the right-hand side shows an interactive HOL4 session where I have already started an interactive proof of the theorem. If we now run NLExplain, notice that the prompt in the read-eval print loop of the HOL4 session changes, which denotes that we're now running an NLExplain session. If we now take our first Lassie tactic from before, which is introduce assumptions, and send that to the HOL4 session, the HOL4 proof will be decorated not only with its showing the current proof state, but also showing the tactic that has been applied on the HOL4 side to get to that proof state. Similarly, we can apply our tactic from before, introducing a new assumption, and if we run it, we see how we could have achieved the very same result with the HOL4 tactic. As you've seen, NL-explain is a perfect fit for understanding how Lassie's tactics map to HOL4 tactics. So let's look at this a little more closer. As before, we send the Lassie tactic to the Sempre semantic parser, which will return its HOL4 tactic equivalent to us, which we can then apply to the proof. However, in contrast to NL-tac, an additional string description of that tactic is returned by the semantic parser, such that we can use it to enrich the printed proof state with the tactic that has been applied to make it easier to understand what has happened. So this makes NL-explain our tool for explaining how HOL4 tactics work with Lassie. Finally, let's look at how the def command works, which allows you to define these tactic descriptions that we have now used. So when defining a new tactic, you will just provide a single example how this tactic may work. At the top of the slide, I'm showing you an example call to the def function. As the Lassie definition, we will use the proof with @assoc string. And here we define proof with to be a decision procedure which calls into two different rewriting algorithms using the provided arguments, and finally tries to solve the goal using the Metis automated prover. This also shows how Lassie can be used by expert users, as it allows us to define tactics that combine commonly used decision procedures into larger ones. After running this through the semantic parser, NL-tac and NL-explain can use this proof with tactic with an arbitrary long list of theorems, even though we only gave one as an example to the semantic parser. This makes def our tool for extending Lassie with a custom tactic description. Coming back to the big picture, you've now seen how Lassie is used, and now I want to shed some light onto how the semantic parser is used by Lassie to develop these tactic languages. As a quick overview, you can conceptually split Lassie into two worlds. There is the front-end Lassie world, which is using NL-explain and NL-tac, interfacing with the semantic parser Sempre. And Sempre, under the hood, has these two big boxes that I'm showing here on the slide. The top part being the core grammar, in which we model plain HOL4 tactics. Using the def command, which sits right in the middle between Lassie and Sempre, as it is our manager for the communication, one can extend this core grammar with new Lassie tactics. Before I'm showing you how this def command works, we have to first look at how the core grammar is designed and how it works. Here I'm showing you an excerpt from Lassie's core grammar used for modeling plain HOL4 tactics. And at this point you may wonder that this looks just like a plain context-free grammar. What makes it semantic parsing here is the addition of these lambda abstractions as so-called logical forms, which are allowed to interpret the parsing result. As an example how this works, in the center, the second rule from the top is our rule for parsing a tactic just as a plain so-called token, which means that we look up a tactic with that name or the token that was recognized from the grammar from Lassie's tactic database. Similarly, this works, for example, for theorem to tactic functions, and then we have combinations of those. By carefully designing the grammar such that it parses a subset of HOL4 tactics, we know that any extension of the core grammar performed by the semantic parser will always be unambiguous. More details about the design can be found in our paper. In the interest of time, I would now like to go into the details about how def works. If we define, for example, simplify with real add assoc to be a call into the fs simplifier with that theorem as its only parameter, Sempre will add two new rules to the grammar. The first rule just being the literal example we just saw, simplify with real add assoc, translates to fs with real add assoc. But if we look a little more closer, you see that the real add assoc is a grammar terminal which can be replaced by its non-terminal counterpart, Theorem. Thus, Sempre will add the second rule, simplify with Theorem as fs Theorem, into its grammar. This generalization is what makes Sempre our perfect fit for developing tactic languages with a semantic parser. In general, Sempre will automatically generalize grammar terminals into non-terminals, adding new rules that go beyond the examples that are given to the def command. Coming back, you have seen how def is used to extend the grammar and what we can do with the semantic parser that was not possible with other tactic language frameworks. What I want to show you now is how the case studies and how the HOL4 tutorial show how Lassie can be used for bigger proofs. First, I will quickly give you some statistics about the case studies. So, in total, we have performed 3 case studies, and on the top of the table here, I'm showing you their kind of descriptive names. One is for proving Euclid's theorem. Then we have one which proves some natural and real number theorems. And finally, we have naturalized a library proof such that it is, in our opinion, more appealing to a novice user. The table now shows the number of theorems we have proven for each case study, the number of tactic definitions we had to perform for proving these theorems, and finally, the maximum number of reuses for Lassie tactics that we found. I want to highlight one point here. Naturalizing, the library proof, was the 3rd case study we performed after doing the first 2, and it turned out that we could just reuse the tactic definitions from the first 2 case studies to perform this naturalization, and we're able to reuse a lot of the tactics. More details about these case studies can be found in the paper, where we also give some code excerpts. But in the interest of time, I want to quickly highlight some of the definitions and show how they work. Here, I'm giving you 3 example definitions from the case studies. The first one just works similar to what we saw earlier, where we define by example a new Lassie tactic, thus add assoc for n, which specializes the add assoc theorem for the natural number n, and then gives a HOL4 equivalent, which is then, as we saw earlier, automatically generalized into a kind of general purpose specialization tactic. The definition in the middle is more interesting. What we do here is similar to the decision procedure we built earlier. We combine, again, 2 rewriting algorithms and the meta solver into a bigger decision procedure, which automatically solves simple goals. The last example on the slide shows how we can then reuse earlier definitions that have become part of the grammar to build more elaborate tactics. For example, show true using add assoc will turn into a general tactic that allows us to prove arbitrary properties by just giving the theorems that are necessary to automatically prove the claim that we want to show, which gives us a nice shorthand description for writing out bigger automated proofs. With this, I want to stop talking about the case studies now and go into the HOL4 tutorial. So if you think back, our initial motivation was that using an ITP system requires detailed knowledge about both the involved proof steps and the tactics that represent these proof steps. And now, looking back at the features that Lassie provides, the key idea was that we can decouple learning the proof steps from learning the actual tactic vocabulary using the functionalities provided by Lassie. First, we will use the def function to define a language which is, in our opinion, more approachable for new novice users. Using NLTag, we can then use our previously defined language to teach HOL4 proof steps without having to care about the actual underlying HOL4 tactics. And in a final step, we can then use the NLExplain to teach the HOL4 tactics without caring about the proof steps because they have already been performed in the NLTag step. Our tutorial is available on GitHub, and I would like to now highlight some of the definitions from our language. So I'm showing you here in the table on the left-hand side some example definitions that we gave and their HOL4 tactic equivalent on the right-hand side of the table. The first few are just as before straightforward simple examples. And then as we've seen before, we define our kind of automated decision procedure solves the goal. What is interesting now is that we can also then reuse that to define a trivial tactic, which just uses no additional theorem, but all of the ones that have been loaded so far into the context to prove a theorem. And similarly, we can then derive additional, more elaborate tactics, for example, true follows trivially at the bottom of the table, by defining it as show true using the trivial tactic, which then just automatically can enrich our assumptions in an interactive proof. To conclude, I have shown you how in Lassie tactics are defined by example using an extensive semantic parser, which removes the need for prior experience in implementing custom tactics. Doing so, extending Lassie's grammar is straightforward for expert users, enabling them to implement custom tactic languages. We have also seen how Lassie's tactics can work as a drop-in replacement for HOL4 tactics, and in the case studies and the HOL4 tutorial, we have seen how Lassie can be used for teaching ITP systems and how it works in bigger proofs. The code for Lassie is available on GitHub, and with this, I would like to conclude my talk, and I'm happy to answer any of your questions during the CPP'21 Q&A session. Thank you.